Okay. Now, can you make it in 45 minutes or maybe max 50 minutes?
Sure.
Because I need to go back. That's very important meeting.
You bring it for me when you come.
Well, I'm not starting until you are here.
You bring it when you're coming.
No. If it's the whole purpose, you have to come here.
Okay, so I'm coming then.
Come in.
Yeah. So you can.
Bit too late, you have eaten everything.
We will start first, okay?
Yeah, I'm coming.
Bring QB with you.
QB.
Yeah. Here's a chair, huh? Here's a chair.
So, what are you going to talk about today?
Yes,
You're a chair. And
advanced conversation approach for early warning detection.
Challenge.
You
Yeah.
want your early
Yeah,
warning
very
device?
challenging.
I have to leave.
Did you bring it?
Today.
Your early warning device, did you bring it?
Whatever you want.
No, it's just a numerical
Yes, I'll
simulation.
talk to you and
Are you sure?
alright.
Mohan is coming.
He didn't bring his early warning device.
Oh, yes.
How can you tell us the stop is going to fail? Also, excuse me, question.
They'll scare him. You're already scared now. He's scared you.
Scared, Ty?
Yeah.
You're scared?
Yes.
No. QB has tough questions. I'm not about.
Yeah.
Come on, you supervisors are tougher than the panel.
We're just scared him before he starts.
With the Mohan.
But that's the one.
He worked earlier, so he takes time.
Right. Yeah. Can we? Alright.
No, you can't stop. Mohan is coming to eat.
Alright, good afternoon everyone. Welcome to TICE confirmation milestone. We have supervisors here and 3 panel members, Yihai and Mohan. I suppose you know the process we are doing here for the milestone. You will have 20 to 25 minutes, give the presentation, and have generous audience ask question. Afterwards, we have the panel discussion, and then your final announcement. Is anyone online? Okay, can you hear us? Online audience?
Was it? Are you online, right?
Mohan, you are online?
No, you're
Yeah.
looking for your hair.
Okay, that's good. Yeah.
Oh, good. Wonderful. Great. If you're ready, you can just get started.
Yes, sir. Thanks. So before to start my talk, I would like to take the opportunity to thank all my professor and panel and all my friends that spend your valuable time to come in today. And welcome to my confirmation presentation. So the topic today is development of an advanced computational approach for early warning and prediction of rainfall-induced slope failures. So this is the content for today, including 7 sections. First, introduction. So rainfall-induced landslide is one of the most common serious natural hazards for hilly slope due to prolonged or heavy rainfalls. It may certainly occur with high trailing speeds, posing threats to human life and properties, including building, highways, and infrastructures. So how has this disaster happened? Basically, we have a slope. The water infiltration into slope due to heavy rainfall, and it makes the soil become saturated with water, it loses its strength, and it means it can no longer support the weight of overlying material, and it becomes unstable and starts to slide downhill. We call it landslide. Osanai et al. 2009 here, they conducted statistical study on 19,000 cases of landslide, and they reported that 93% of those landslides was caused by heavy rainfall. According to International Disaster Database, more than 62,000 deaths with a total loss at least 9.7 billion US dollars since from 20th century due to the rainfall due landslide. And furthermore, global climate change had triggered high frequency of rainstorm together with fast population growth with improper settlement development. It makes this disaster more and more harmful impact to the community. So for us, like academy or geotechnical engineer, what can we do to minimize this problem? So among various methods, the monitoring and early warning system are considered to be one of the most promising way. So this is the illustration of the rainfall induced landslide early warning system that you can see over here by Uchimura et al. 2015. 2017, Cavallo here, he plot the components of rainfall induced landslide. In here, I want to highlight that when we're talking about this system, they have the technical part and the non-technical part. Example of non-technical part is communication and education. It means how you send the message to the community and how do they understand. Emergency plan is when the disaster going to be happen and what the people should do. So in my project, we focus on the technical part and we make this research question. So with the input information such as soil properties, water pressure we get from sensors, we generate the initial condition. And with the rainfall data we get from the rain gauge or from weather forecast, example 2 weeks, how can we use the advanced computational approach that can predict when, how, where that disaster occurs? So in here, we want to emphasize the information of beyond the onset of failure. It means that we can detect when the failure happens, and we also want to know that the destruction zone, what it impacts to the community. So literature review. Firstly, let's answer the question, how has rainfall induced landslide been modeled? Commonly, the traditional LEM, ABM may be two of the most used numerical tool to study. Example you can see over here, 2017, Zhang et al. Simulate the rainfall of seabed analysis by the finite element method, and they're using the information incorporated into LEM over here to calculate the factor of safety or also estimate the critical slip surface. 2021, Citaniers over here simulate the rainfall induced line. In here, they also incorporated the advanced unsaturated constant model, and their prediction compared with the sensors on the field, and then they can detect the failure. So it has been successful in several practice applications, but it should be noted that it has some limitation. The well-known issue named mesh distortion. So the limitation I want to highlight here is most of the efforts of both, they have been limited in the failure initial stage. That is where we have small deformation. So from the point of view, to overcome the mesh distortion issue and simulate large deformation problem, the method over here, MPM, PABM, or HBH, the smooth particle hydrodynamic, a mesh-free continuum method might be a better choice. It has been proved that this method that you see over here have great capability in dealing with rainfall and landslide with large deformation. And I also would like to emphasize in here that each of the numerical tools, they have their own advantages and disadvantages. No method is better. For example, if I'm looking for the safety design, I could definitely choose the finite element method in previous slide. But if I'm looking something extremely large deformation, then I could have the option of MPM, PABM, or HBS over here. And in this project, based on our resources, the fully validated HBS framework is selected and continue developed. And in here, I want to show you some limitation. Currently, still lacks the incorporation of advanced constant model to properly simulate unsaturated soil behaviors. The second limitation here is these studies above here are deterministic without considering the geotechnical uncertainty. So it's meaning that the spatial variability of soil properties, it makes significant effect to landslide failure, landslide property, and risk assessment. So how has the geotechnical uncertainty been considered in rainfall landslide modeling? First, take a look to this picture. So profile of the natural slope are unlikely to be completely uniform due to the complex deposition and alteration process. So even with so-called homogeneous soil layer, soil properties tend to vary from one location to another, and we call it the spatial variability. So the first pioneer work we can name is from Professor Fenton and Griffith over here, 2008, when they incorporated the random field into the finite element method to have the academy or geological engineer to do the slope analysis After that, doing for rainfall-induced landslide analysis. So from our gas, this is the AM31. First, we incorporate the advanced unsaturated quantity model random field into the state-of-the-art of HVS. Second, we develop the novel algorithm to create suitable initial slope conditions from limited data and using physics-informed random field. So finally, we combine all the tools together and we establish the failure criteria. So the contribution, I'm really excited to share with you about my project. First key thing here is, this is the advanced knowledge and computational framework that can predicting entire rainfall-induced landslide using the spatial, considering the spatial distribution and using the limited data input. Also, the key second thing here is, this is a valuable tool and the failure criteria we established from here can incorporate it to the current rainfall-induced landslide early warning system design that can produce better warning, thus reducing the damage of structures and the loss of lives. Proposed research plan. So in here, in my PhD journey, based on the gap, I make it 3 steps. The first step, we incorporate the advanced model random field into HVS framework. Second, we reconstruction field data from limited measurement. Finally, we combine all of them together and establish the failure criteria. Research methodology. So first, we develop couple of HVS framework with advanced saturated quantity model. So we start from the multi-phase mixture theory when we have the mass conservation equation, momentum conservation equation, and then by solving the equation, we get the increment of power pressures, or by summation of all momentum equation of each phase, and we get the increment of velocity. And to solving the equation, first we need to stress-strain relationship by using this quantity model. We also need the degree of saturation and water permeability function. Finally, to solving the equation is, this is the spatial derivative. This is the way that we need to using HVS. So what is the HVS method and how does it work? So the HVS method here is the mesh-free continuum method that can, in which particle will carry the field variable and move with the material velocity. Second, we incorporate the random field into our framework. So what is the random field theory? So random field theory here is mathematically framework that can model the uncertainty. So if you want to learn about random field, this is the 2 picture that you want to understand. The first one we call it the PDF, which is the probability distribution function. So in here, they will give you the information like central tendency or the spatial variability, which can represent by mean, variance function, or standard deviation. The next picture over here can showing you the spatial correlation. We call it the covariance function. So after all of the things, we're choosing the method and we can generate a numerical field like this, and we assign to our particle in our numerical tool that we're choosing. So the final here, this is where we develop novel algorithm to create suitable initial slope condition for limited data. So when we make this question, what if we actually only have very few measurements of our system? So in here, I can showing you one example. The first example, we have a blur picture, and then we want to know what is the original picture, or we just had to input like one borehole, and then we want to know what is the whole field data. And in this case, this is a problem well known called the underdetermined problem. And in this case, that basically you had to input is just a small vector, but you want to output like the very tall vector. It means that you have the infinite solution. And to deal with this case, we're using the optimization algorithm to find a particular solution. So in our project, first we're using combination technique. In here, basically, we have the input limited. We do the optimization. We figure out what is the pattern hidden chain in here, and we predict the output. And also, the artificial neural network will be used. Basically, this is a set of optimization can help us to improve our prediction. Preliminary research. So in here, first one, we validation with one dimension transient seabed flow. So in here that you will see, this is the initial condition. This is the 3-meter high soil column. The flux positive over here represent for the rain. The negative flux over here represent for the sun, which is infiltration or evaporation, and we compare with the analytical solution. Next, we validate with the two-dimensional change-seabed flow against experiments. So this is the experiment setup from Keaton Gray 2007. And the list parameters here allow us to calibrate our soil water cavity curve. And first, we compare results with the finite element method. So you can see from here the excellent agreement between the two numerical methods, suggesting that our developed HVAC model could capture well the change in seabed flow, not only iso2b, but also anisotropic. And next, you can see here we compare with the experimental data. So this result that you can see represent for the data, its location from 1 to 5. This is the sensor over here. This is from 6 to 10. You can see from over here. So in the next step, I'm going to show here is coupled seabed flow deformation. First, we start with the advanced saturated consistency model, following the chill technique here with the real Lincoln soil sample. And then we do the numerical test, compare with the experimental data to see the performance of the model, and we incorporate it into HVS. First, we do the simple shear test with a constant volume shearing, and then you can see over here the excellent agreement between the single element solution and the HVS solution over here that can prove that our incorporated is correct, and we start to conduct the large formation. In here, with the large formation case study 1, the validation against of Rillingen field experiments. Here, this is our model setup. The parameter here basically can have a calibrate soil water cavity curve, and this is our result that we get after the rainfall, and then we have this collapse, and we compare with the instrument or to compare with the sensor on the field here. So in here, the green line represents for the HVS solution. The red over here represents for the sensor that you see over here. And we also capture question 9 with the displacement evolution. The second validation case here, rainfall due landslide experiment from Denso that you can see over here. Then this is our model setup. And again, parameter here can help us to calibrate our soil water curve. And this is the result. So in here, after rainfall, we compare with the suction evolution and also the detect when the failure happened. Or also in here, we can detect the final runout distance compared with the instrument landslide over here. So the final result, that's so really interesting, like the other part I want to share here is reconstruction random field. That is the way that we're using the optimization. We start from some simple signal with the limit data input, we reconstruct it. Also the friction angle with haze that you can see over here. And then we start with the slope, the numerical field. So basically in the field, we dig one borehole. And basically the information from the field, we didn't know, we just had a one borehole information. And then from this information, using optimization, we predict the other place in the field. And then we construction with our solution. We compare with the neural field that we generate basically to evaluate our result. And then 1 borehole, 2 borehole, 4 borehole, 5 boreholes. The more borehole information incorporated, the better of the solution that we can have. And then we also incorporate in here with the slope with 2 borehole, we reconstruct here. We also set up some sensors basically to take these advantages to doing my next step. So I take the information to make the prediction better. Sunlight. So this is the work that I'm doing in the past. This is the work that I'm doing in the future. Acknowledgement. First of all, I want to thank all my supervisors, especially my supervisor Havui for endless support. Also, not only study, but also life. Thank you, panel members and my friends that spend your valuable time for me today. I'm so grateful. Thank you.
Great. It's great to join us all these questions. Any questions from your friends?
Thank you for your very fantastic presentation. So you mentioned that your object of your project is to develop a failure criterion that can be used for the engineer design for rainfall-induced drop failure. But to my best understanding that to develop a criterion, you need a lot of data or case study. So if you don't have that much data, how can you make sure the criterion you develop is reliable or meet the engineering standard?
Yeah.
Thanks.
Yes. So, thanks. That is the case that we want. That is why we start from the numerical field data we generate. So we call it the hidden layer that you see over here. So normally in the field it's limited, right? Correct? But in here, because we start from numerical field, that we have the data already is basically hidden, and then we're using our development solution to basically validate our solution.
So you mean thanks. So you mean you using your numerical methods do a lot of simulations that adds your data to develop the criteria?
That you can see from this slide over here. That is where we generate like the field incorporated with random field, because in the actual field the soil pretty distributed, right?
Yes.
And that's why we generate the numerical field that represent for the field to evaluate our resolution.
Oh, I see. Yeah, thanks.
Yeah, thanks.
Any further question? Because Habu is leaving shortly, so probably online audience, any questions? No. Okay, so probably move to next stage for the panel discussion. But can I ask also thank you for coming.
You're on your own now.
Can you check if any online audience?